Hi class, we're now on chapter 11.9. We're going to be looking at mixtures of gases. So we're going to be looking at partial pressures, and based on the kinetic molecular theory, each of the components in a gas mixture acts independently of the others. What this means is that if you have several gases in a container, they will each behave as if the other gases are not there, and they are in the container alone. What we want to know is that if we have several gases, they each exert their own pressure. So this is where we call this partial pressure. A partial pressure is for one gas, and we add all the gases up, and that will give us the total pressure in a container. So if we look at our atmosphere, our air is made up of 78% nitrogen, 21% oxygen, 0.9% argon, and 0.04% CO2, and a few other trace gases. So all of these gases each create their own partial pressure, and we add them up together, and we know what the total pressure of the system of our atmosphere is. So for instance, nitrogen makes up 78% of the total pressure. It acts in our environment as if it's the only gas that exists. It doesn't interact with the other gases. They do not mix together. They all act independently of the other gases being present. Same for oxygen. Oxygen is 21%. It acts as if it's the only gas in our atmosphere. So this partial pressure, it's also called Dalton's partial pressure, though your book doesn't refer to it as such. It indicates that a pressure depends on the total number of gas particles, not on the type of gases, not on the type of particles, excuse me. So if the total pressure exerted by the gases is a sum of them. So here's the total. So if we were to take the atmospheric gases and change these, we would take them as a partial pressure and add them up together till we get to the total pressure of all the gases together. So here's an example. We have partial pressure of helium is 2.0 atm, and you can see it's in a container by itself. We have the partial pressure of argon, which is 4.0 let's just say the pressure of argon is 4.0 atm, and it's by itself. But when we add them together, the pressures do not change for these gases. They act as if they are in this container alone and not in the presence of another gas. So we add them together. So the partial pressure of helium and the partial pressure of argon equals the total pressure at 6 atm. So that's what this formula here represents. So if we go back to the air that we breathe, we see that nitrogen has a partial pressure of 594 millimeters mercury. Oxygen has 160. Carbon and all these other trace air gases is 6. And this makes a total of 760 millimeters mercury. You can also see where the percentages break down. So what we call atmospheric pressure is actually the sum of the partial pressures of the gases in the air. So partial pressures, we take the fractional composition. The fractional composition is the percent composition divided by 100. What that means is that when we break this take it out of percent, we have to divide it by 100. And that gives us, in a sense, a decimal form. But we have to multiply it by the total of all the gases. So what this means is partial pressure of a component, fractional composition of a component. This would be the percentage changed into decimal form by dividing it by 100, which is what we could see here for 80% of helium in this container. Then we multiply it by the total pressure of all the gases, which is 1 atm. So 0.80 times 1.0 atm equals 0.0 atm, because before this there is no units with this fractional composition of the gas. Same goes for neon. We have a partial pressure of neon is 0.20 atm, but it's given to us in percentage form of 20%. We divide that by 100, times it by the total pressure, and that gives us our 0.20 atm. And if we add these together, that gives us the total pressure of the system. So let's continue on with this. If we are given, we change the percentages of our atmospheric pressure. So in this case, we have nitrogen that is 0.78 atm, and we get this from the percentage by dividing it. So here, if we look at this, we have this and divide it by 100, it'll give us the decimal form. Here we have the oxygen, do the same thing, and we have argon. We add these all together, and they equal 1 atm. So let's do some problems. A mixture of helium, neon, and argon has a total pressure of 558 millimeters mercury. If the partial pressure of helium is 341 millimeters mercury, and the partial pressure of neon is 112 millimeters mercury, what is the partial pressure of argon? So we pull out what we know. We know the total of the whole system. We have a partial pressure of helium at 341 millimeters mercury, and we have a partial pressure of neon at 112 millimeters mercury. But we need to know the partial pressure of argon. So we take the formula that we have here. So we have a partial pressure of helium, neon, and argon. And now we can start plugging in the values that we have. So here we have, and we solve for argon. So we have our total, which is right here, and we have our partial pressure of helium, which is 341, and then we have our partial pressure of mercury, which is 112. That will tell us that our partial pressure of argon is 105 millimeters mercury through the subtraction from the total of the system. So let's do another one. A scuba tank contains oxygen with a pressure of 0.50 atm and helium at 855 millimeters mercury. What is the total pressure in millimeters mercury in the tank? Now, we're given two partial pressures, however they are not in the same units. So it's telling us we specifically want our value in millimeters mercury. So we first have to convert our atm to millimeters mercury, then we can add these together. So we have to use a conversion. In this one, we use the conversion of 1 atm is equal to 760 millimeters mercury. Plug that in. So we start with our 0.50 atm, set up the conversion, and we end up with 342 millimeters mercury. We then can now add these together, and the total pressure for the system is 1.20 times 10 to the third millimeters mercury. All right, so another problem. For a deep dive, a scuba diver uses a mixture of helium and oxygen with a pressure of 8 atm. If the oxygen has a partial pressure of 1280 millimeters mercury, what is the partial pressure of the helium? So in this case, it's telling us it still wants it in millimeters mercury, so we have to also do another conversion. So we convert the 8 atm using the same conversion, and we end up with 6,080 millimeters mercury. Now, we can take this 680 millimeters mercury, which is our total system, and subtract the partial pressure of oxygen, which is the 1280 millimeters mercury, and that leaves us with an answer for the partial pressure of helium is 4800 millimeters mercury, or 4.80 times 10 to the 3 millimeters mercury. So this answer would be C. Calculate the partial pressure of oxygen that a diver breathes with a heliox mixture containing 2% oxygen at a depth of 90 meters, where the total pressure is 10 atm. So there's a lot going on here, but really this is not a difficult problem. It wants to know the partial pressure of oxygen. So the first thing we need to do is get out of the percentage. It's also given us the total pressure, so this is not as difficult as it may seem. We want to get the partial pressure of oxygen, but we know the percentage of oxygen. So we pull the 2% out of the oxygen, and we have a total of the system at 10 atm. So remember, the partial pressure of a component is equal to the fractional composition of that component times the total pressure. This is very similar to what I already covered. If we go back enough, right here. We're doing the same exact step. It just is in a problem that seems really wordy and might seem intimidating, but it's really nothing more than what I've already shown you. So in this case, we take the percentage divided by 100. It gives us our fractional composition, and then we multiply that by the total pressure of the system, and that gives us our partial pressure of oxygen is 0.20 atm. So this is not a difficult problem. There was a lot of information there to make it more wordy, to seem like it's intimidating, but it really isn't. Okay, so now we look at vapor pressure. So when a gas from a chemical reaction is collected through water, so sometimes reactions occur in water, in solution, and the water molecules get stuck and attached with the gas. So when you're trying to determine the partial pressure of the gas, you now have the partial pressure of water molecules attached to the gas. So we need to remove or subtract the water molecule, the partial pressure of the water vapor in this. So if you look here, you can see that this reaction happens in this sealed tube, but it's got an outlet, and the the hydrogen gas is evolving, and we force it through this water molecules to end up being in this dry part of this upside down beaker. So what it does is it comes through and it pushes the water is attached, not attached, it's filled to the top. But as the gas comes through here, it pushes the water out of the way, and the hydrogen gas is left in this, what it looks like an empty space, but it's really filled with hydrogen gas. But what we don't also see is that water molecules have attached themselves to the gas. So we consider this like a wet gas, and we want a dry gas in order to calculate the correct partial pressure. So this is not a difficult thing. This is actually really easy. It has to do with partial pressure. So in this case, we have the total gas, the total system, the pressure. We want to know the partial pressure of the gas. We have to look up what the value is for the partial pressure of water vapor. We don't even have to do anything. We have to look up a chart, and that'll tell us what our water vapor is, and then we simply subtract it in order to determine what the partial pressure is. So in this case, that's what it says. We just look up the value. It's not anything more difficult than that. So here, let's do a problem. Hydrogen gas was collected over water at a total pressure of 758 millimeters mercury and a temperature of 25 degrees Celsius. What is the partial pressure of the hydrogen gas? So if you look up the partial pressure, we have to look up the temperature. That's the most important part. And it tells us that the partial pressure of water vapor is 23.8 millimeters mercury. So that's all we have to do is look up the temperature and look at the chart, and it will tell us what the partial pressure is for the water. Now we plug in what we know. We have the total pressure at 758 millimeters mercury. We want to know the partial pressure of hydrogen, and we know what the partial pressure of water is. So now it's just a matter of subtracting, and our partial pressure of hydrogen is 734 millimeters mercury. So let's do another one, very similar. These don't really change very much. The oxygen gas, I mean, they can make them harder in other ways, but to determine the vapor pressure, that's just looking up a chart. The oxygen gas emitted from an aquatic plant during photosynthesis is collected over water at 30 degrees Celsius and a total pressure of 753 millimeters mercury. What is the partial pressure of the oxygen gas? We handle this the same way. We have, I messed up on this one. This should be 753 and I put 758, so this number is going to be off by a little bit. But hopefully you understand the steps. So this should be 753. Then we have we want to know the partial pressure of oxygen. If we look at 30 degrees Celsius, it's 31.8 for the partial pressure of water. We do the subtraction, and this is 726 millimeters mercury. However, if we were to take the correct value and subtract from it, it would be 721. So this value should actually be 721 based on this value here, but I forgot to correct this. But that's it.